So good evening everyone. Maybe we can start for today. So today we'll be discussing the major aspects, like we'll start discussing the major aspects of linear dynamical systems, which basically starts out by venturing into the topics of controllability, reachability, and so on. So up till this point, whatever we had discussed, they were like kind of the preliminary stuff, finding the state space solutions and determining stability of the state space using eigenvalues and so on. Those were kind of, in some sense, an extension of the classical control things that we had learned. But now here we'll be entering into some really new domains, which is separate from the classical control arena. Okay, so with that, we'll start doing some questions. Okay, so okay, to keep these sessions as interactive as possible, whenever we have a problem, we'll first uh, put write the state the whatever the problem asks us to do. We'll clearly state that first, and then we'll wait for some time. I'll wait for some time till you guys maybe solve it or try something out. And if possible, you can put the answers in the chat box, or if you have any doubts, you can ask me, and then we'll discuss the answer together. So that way, all of us can benefit as much as possible from these sessions. Okay. So first, for the first question, yeah, we have, let P be some M cross N matrix. Then we want to find out which of these statements is true. Is anyone familiar with the rank nullity theorem or the fundamental theorem of algebra?
Yes, sir.
Okay, so can you state those?
So rank.
Try to state all, because these are kind of very fundamental to whatever we'll discuss further. Yeah, okay, I'll just give the statements first.
Sir, number of independent row or column is known as the rank.
Yeah, that's true. So, based on that, there is a theorem named as rank nullity theorem, which states that let A be some M cross N matrix, then the dimension of column space of A plus the dimension of null space of A is equal to N. This is the rank nullity theorem. So, this kind of gives us the rank of A, and this kind of gives us the rank of the null space of A, which is referred to sometimes as the nullity. Like, it's just a terminology, but yeah. So that equals the dimension of the space on which the transformation is being occurred. Like A acts on an Rn vector, so here we'll have n. Alright, this is rank nullity theorem. Then there is something known as fundamental theorem of algebra. Of linear algebra. Sorry. So as per that, very loosely speaking, let the dimension of the column space of A be denoted by R, which essentially gives us the rank. Then n minus R is the dimension of the null space of A. R is also the dimension of row space of A, because rank is same for the matrix, row space or column space. And then M minus R is the dimension of the left null space of A. Okay. So then using these, we get another result that says that the row space of any matrix, any M cross N matrix, the row space of any such matrix is perpendicular to the null space of that matrix, and the column space of a particular matrix is perpendicular to the null space of its transpose. Okay, so now based on this result, based on this result, which one do you think is the correct solution among these? Okay, any more guesses or answers? Is everyone familiar with the concepts of row space, column space, null space, left null space?
Yes, sir.
Okay, so the row space, I'll just for brevity, I'll keep it here. Let this be A matrix. Then we'll have some rows and some columns, right? So the space, vector space created by a linear combination of the rows is known as the row space, and a vector space created by the linear combination of columns is known as the column space. And null space is the space of all vectors. Let's say all vectors x such that a into x gives us 0. Okay. And similarly, null space of A transpose, which is known as the left null space, is basically all space of vectors x such that A transpose x is 0. Let's keep this as y. Okay. So then based on these definitions, the image of P, any matrix P, is just the column space of that matrix. The kernel of P transpose is the null space of P transpose. This is null space of P. This is the row space of P because we are taking P transpose and its column space. So we get the row space. So now this option seems to be the correct one based on this statement for the rank for this theorem that we have. Okay, is it clear? Shall we move forward?
Yes, sir.
Okay, now we have this question. So given A, some 2 cross 2 matrix, square matrix, we want to find out the value of A square minus 4A plus 3I. Alright, so what should this be? Let us calculate this. Maybe we'll take some 3 minutes around to find the solution. Once you have the solutions, please put it in the chat box. Yes, there is a poll live for you guys. So once you have the answer, please like mark your answer. Yes, okay, let's wait for the others to do it. Okay, so Kushbu, can you tell me how did you do it?
Yes, sir. First multiply A into A, then
Okay, how much do we have here? This is correct, right?
minus 4A.
Yeah. Okay, so now we just sum these up and we get our solution. 4a plus 3i is equal to 1001. Okay, for a 2 cross 2 matrix case, it is a very simple solution. Like we can always compute it ourselves and maybe even for 3 cross 3 or maybe even up to 4 cross 4. But what if we had a really large matrix, let's say 9 cross 9 or 10 cross 10, something like that? Then how do we find solution to problems of such kind? So one very useful result in such situations is the Cayley-Hamilton theorem. So what this says is every square matrix satisfies its own characteristic equation. Okay, so what does this mean? So for any matrix A, what is the characteristic equation? It is given by determinant lambda I minus A equal to 0. So this equation is known as the characteristic equation. So let's find it for this matrix. We have lambda minus 1 minus. Right. So when I say a matrix satisfies its characteristic equation, it just means instead of, so whatever variable is there in the characteristic equation, here it is lambda, just substitute the matrix in that and the expression will still hold true. So that means we'll have a square minus 4a plus 2, but obviously in a matrix we cannot just add a scalar to it, so here we'll just have identity and that equals to 0. So now see how powerful of a result this is, because we wanted to find out a square minus 4a plus 3i, and finding the characteristic equation is much simpler than solving these things, a square 4a 3i, at least for substantially larger matrices. So here we have the characteristic equation that gives us this expression, and then from there we directly have that this is nothing but a square minus 4a plus 2i plus I. So this is nothing but 1 0 0 1, right? Is it clear?
Yes, sir.
Okay. So I hope this concept of Cayley-Hamilton theorem is clear. If not, then you can just ask. So maybe just one minute. Yeah. So you can also always verify such things on MATLAB to check whether what you're doing is correct or not. I'll upload the same MATLAB code file onto the cloud. Like it will be shared with you guys. So then, yeah. So is this clear? Yeah. Okay. So we'll move ahead. Now we are given an LTI system. The A matrix is given and the B matrix is given. We have to find out whether it is controllable, uncontrollable, or what is its nature. So can someone tell me how do we determine whether a given state space system is controllable or not?
So
Yes, someone tell me.
if, if rank is equal to determinant of A, then it's controllable. If not, then not controllable.
No, I'm sorry, I don't get you. If rank of
It's number of order of controllable matrix is equal to the order of A, then it's controllable. Otherwise, not controllable.
right, so basically, if rank of the controllable matrix C is n, where let's say yeah A is Rn cross n, then the system is controllable.
Yeah.
Right?
Yeah.
So so okay, let us find the controllability matrices then. We'll take some time to do that. Now, once you have the solutions, you can post it in the chat box by making some square brackets like this, let's say, for example. Yeah. So you can post the commas, show one particular row, semicolon takes us to the next row. So once you're done, please submit your answers on the chat box. Okay, so we have one answer. We'll wait for some more time to get if others are able to solve it.
Sir,
Yes.
sir, I have two questions. Can ask in last of class?
Yeah, sure.
Okay, thank you, sir.
Is it related to the current question? Then you can ask right now. But if it's a
No, sir, no, sir,
okay,
subject
yeah,
related.
yeah, okay. Okay. So Aman, can you tell me what is like how do we find out the controllability matrix?
So B matrix, AB matrix, A square B matrix,
Right. So
RC order.
yeah. So for any general nth order system, we have it as VAB up to 8th bar n minus 1
Plus
B.
N minus 1 B.
Yeah. So let us find out for this case. So B is obviously this one. Let us find out AB. Right. Then let's find out A square. Okay. A square B is just A into AB. So we can just find this one out. Two. So is this correct? Did I make a mistake anywhere?
Yes, sir, correct.
Okay. So then to determine whether this is controllable or not, we have to find out the rank of the controllability matrix. So rank, so there are a few ways we can use to determine whether any given matrix is full rank or not. First is to find out the determinant. So we know C is 101, 111, 212. So the determinant is we can take along this column. We have 1 into 2 minus 1 plus 1 into
-2, -2.
Yeah, is this correct? Yeah. So we have
Yes, sir.
-1 plus, sorry, 1 minus 1, that is 0. So this now tells us that the matrix is at least not full rank, right?
Yes, sir.
Then how can we find out specifically what the rank of the matrix is? That we can do it by, like, if,
Echelon method.
uh, sorry,
By echelon methods.
yeah, but for this matrix, we have a very simple solution. We have this column 1, column 2, column 3. Can anyone tell me alpha 1? Can anyone tell me what alpha 1, alpha 2, alpha 3 are that satisfy this particular equation? You can clearly see some relation between these three columns. Like adding any two or subtracting any two should give us the other one.
So
Yes.
C1 plus C2 equal to C3.
C1 plus C2 equal to C3. Yeah. You can see that clearly here. 1 plus 1 is 2. 0 plus 1 is 1. 1 plus 1 is 2. So, so basically what this expression tells us is they are linearly dependent because there exist non-zero alpha 1, alpha 2, alpha 3. Alright. So here, yeah. So first is the system is not controllable. No doubt about that. But then can we also find some eigenvalues and tell that because there are some non-negative eigenvalues or strictly positive eigenvalues, so that the system is clearly uncontrollable due to those eigenvalues. So let us find out the eigenvalues of this A matrix, right? So we'll take the determinant of lambda minus 1, 0, 0. Yeah. Let us try to solve this for a few minutes. Then we'll resume. Please put in the solutions for the eigenvalues in the chat box. Okay, we'll wait if maybe someone else tries this. Okay, we have another solution. Maybe we can try it now. So if you see, we can just write this as Yeah, then I have plus like that. Is this the characteristic equation?
Yes, sir.
Yeah. So, okay, seeing this, we clearly have lambda equal to 1 is one solution, because when I plug in 1, 1 minus 2 plus 1, so it is one solution. So that means, okay, obviously it is, because the characteristic polynomial is this. So lambda equal to 1 is one solution, and then the other solutions we'll get from this thing. So we have, so if we calculate this value, one is 1.618 and the other is 0.618. Okay,
Yes, sir.
it's no, no, it is a negative of 0.618. Yes. So we have three eigenvalues, 1, minus 0.618 and 1.618. Alright. So since two of these eigenvalues are strictly positive, we know that makes a system uncontrollable. Like not uncontrollable, but like non unstable. Alright. So we have that the system is uncontrollable, and like this makes the system unstable. That's all. Okay, so the system is uncontrollable, and and by itself, as an autonomous system also, the system is not stable. So it's like we can't do anything good, like we cannot try to control it in any desirable way for this particular system. Is it clear?
Sir,
Yes.
so how find stable bit? Option number 3.
Sorry,
हम सर स्टेबल ये स्टेबल ये
stabilizability,
लेवल कैसे निकाल सकते हैं? ऑप्शन कैसे निकालेंगे सर?
ये
कोई
वाला ना.
मैट्रिक्स 3 to 3 का दिया हुआ है.
हाँ, तो I think this will be covered in a later week perhaps. Maybe we can wait till that point.
ओके सर.
And then we'll go through. Yeah. So, okay. Now we'll move on to the next question. Given an LTI system in the state space form, this is the system we had earlier, which of the following states are reachable? Okay, so can someone define me what reachability is? Reachability and controllability of a system.
So means
Yes.
move toward origin from any point, say x not t.
That is what? Controllability or reachability?
So reachability.
Okay, 1 minute. So you are saying reachability is moving towards origin or away from
Yeah.
origin?
Origin, yes sir. I think.
Towards origin. Okay, what do you think controllability is?
So move from origin to toward point.
Okay, so you just actually swapped the definitions, no issues. So reachability is just moving. Reachability is basically controllability, controllable from origin. So reachability is controllable from origin, and controllability is controllable to origin. So basically a system is told controllable if you are at any starting initial position and you can control the system, that is you have a control signal that when you provide to the system, the states of the system will go to origin in some finite amount of time. Okay, and for reachability the case is opposite. You start out at the origin, and given any point that you want to reach, you can reach there by providing a particular some control signal. So what reachability says is there exists some control signal so that you can reach to some desired position in a finite time. So those are the definitions of reachability and controllability. So does anyone know what reachability and controllability gramians are? Yes.
फार्मूला पता है
Yeah, formula only.
phi t naught t1 plus integration t naught to t1. Yes, sir. B tau u tau differentiation d tau
Sorry,
dt sir dt
नहीं but ये किसका formula बोल रहे
sir reachability.
हो? Okay, like I'll just 1 minute. So the reachability gramian is given by this term, okay, d tau t naught to t1. So t naught is the starting time, t1 is the time when we want to end it, and this particular expression is under the integral, and this entire thing is known as the reachability gramian. Okay, then we have t naught to t1, almost the same thing, just a minute difference. This is t1. Okay, so this is almost the same thing, just that we have a difference of, instead of t1 we'll have t0. That gives us the controllability gramian. So a little, just 1 minute. Yeah, so what some powerful results about these say? First, okay, so from the definition of reachability, can someone guess the definition for a reachable subspace? Reachable subspace, what could it be?
Means is a part of the subspace of is a part of the reachable sub reachable.
Yeah, so in some sense, any vector which is reachable from the origin for this particular system is an element in the reachable subspace. Okay, so we tell that the reachable subspace, we denote it by something like this. The reachable subspace is given by the image of the reachability gramian. Okay, and similarly the controllable subspace, that is all the initial points from where if I start, I have a control that can take me to origin in finite time. All such vector points, that constitutes the controllable subspace, that is defined as the, well, that is not defined as, we can prove it as being equal to the image of the controllability gramian of the system for some finite time t naught t1. Okay, and further, for continuous time LTI systems, both of these are same and they are equal to the column space of the controllability matrix, the image of the controllability matrix. So this is reachable subspace equals to the image of controllability matrix, which is equal to the controllable subspace. All right, this is a very powerful result for the continuous time LTI systems, right? So from that, how can we determine which kind of states are reachable for this particular system under consideration? We have this result. How can we use this result to find this solution? Okay, try to think about it a little. So when we say when we ask the question which of the following states are reachable, we essentially want to find out what is the reachable subspace. Alright, because if I get the reachable subspace, then I basically know all the vectors in it. So I know all the vectors that are reachable for this system. So I want to find out the reachable subspace, right? So how can I find it out from this result?
Sir, rank calculation?
Sorry?
Rank calculation? From the rank calculation?
Huh. From rank calculation of what?
Matrix A.
No, but from rank of matrix A, what do I get?
Sorry, sir.
No, no, just tell me what do you think about it? From rank of A, how can I get this?
No, I think from rank from A, we compare multiply from B into A like controllable.
Yeah, okay, so we directly can do one thing. I want to find this subspace, right? And I am saying it is equal to this subspace, column space of C. So
Yes,
usually finding the controllability matrix is much easier, right?
yes, sir.
Okay, so what we have established is the reachable subspace is equal to the image of the controllability matrix. So first let us find out the controllability matrix. But I think we found this out for the previous question. Yeah, it's the same. Where is that? Yeah, this is the controllability matrix. Okay, so what is the column space of this matrix? Can you give me a vector for the image of this matrix? Okay, so are you aware about what the column space of a matrix is?
I think the column of matrix
Uh-huh. Column of matrix, then.
like C1, C2, C3, three column, three
Uh-huh.
subspace.
So we have C1, C2, C3, right?
Yes, sir.
Then the column space or the image of this matrix is basically all vectors of this form where alpha 1, alpha 2, alpha 3 are some real numbers. All right.
Yes, sir.
So how can we represent the column space? Like, can you provide me a basis for this column space of the this controllable matrix, controllability matrix? So my question is, let me just frame it once more. I have I am given this controllability matrix, right? I want to find the image of this controllability matrix. Okay. So, and I say that the image is defined as all possible linear combinations of the three columns of the controllability matrix. Okay. So, can you provide me some vectors? You know what the basis for a vector space is, right? So, let's say we have R3, then one of the bases is R3 is span of 1 0 0 0 1 0 0 0 1. So what does this mean? It means that any vector in R3 can be represented as a linear combination of these three vectors. Okay, similarly, can you provide me a basis for the image of the controllability matrix.
How to calculate? Do not know, sir. How to start?
Okay, so let us think of it this way. Okay, let's take some simpler examples. Okay, let's say we have R2. What is the basis of this?
Identity matrix.
The identity matrix, but okay, let's just, yeah, it is the identity matrix, correct, but let's not think of it that way. So let's say we have some vector space V, then a set of vectors V1 till Vn is said to be a basis for V if first is we want all of these. Okay, let's set of linearly independent vectors V1 to Vn is said to be a basis for V if for all vector V in this set capital V there exists alpha 1 till alpha n real numbers such that V can be written as some linear combination of these n vectors. Is that clear?
Yes, sir.
Okay, so now on this basis, tell me what the basis for R2 will be. I want to find a set of linearly independent vectors. Okay, so that every element in R2, I can write it as a linear combination of these new elements. So tell me, you were telling the answer earlier. What was it?
Identity 1001.
1001.
One.
So not the identity, but these two vectors,
Yes, sir.
1001. Yeah. So why is this? Because if I take any x in R2, then I can write it
Linear form. I work.
this alpha 1 C1 plus alpha 2 C2. But okay, let us try to prove this. Can you prove it? How do we do that?
So left hand side, we assume one column matrix x1, x2,
Yeah,
and another side x2 equal to this matrix 1001. Yes, sir. Alpha 1,
alpha 1.
alpha 2.
Okay. So yeah, so basically it is very direct only. You have any x1, x2, then you can find two scalar values x1 and x2 whose linear combination of these two columns will give me the entire space. So now think of this matrix. Okay, I'm saying the image of C is all vectors of the form like this. So tell me, let's try to think what these vector like a basis element should be.
Sir,
Uh,
1 0 0 0 1 0 0 0 1.
wait. Tell once again.
So 0, no, 1, 1 0. So 1 नीचे 0
0. Uh,
0
okay.
1 0.
No, no, I don't get. First vector is what? 1, 0, 0.
Yes, sir.
Okay, second vector is
So 0, 1, 0.
0, 1, 0. Third vector, or is this all?
Sir, another, sir, 0, 0, 1,
0, 0, 1.
I think.
Okay. So, so first is uh, okay. The, so okay, if we take any x in the column space of the controllability matrix, I can always represent it by a linear combination of these three vectors. That is correct. So x is how do we put this? So because x is a vector in R3, this is always possible because this is the basis for R3. But okay, let us think of it this way. Let's take a basis of 101 and 111. Okay, so I am saying all vectors such that they are spanned by these two. Then is there any connection with this vector space and this vector space? Yeah, is there any connection between these two? Okay,
Yes, sir.
so what is the connection?
So alpha 1 equal to 1, alpha 2 equal to 1, alpha 3 equal to 0.
No, yeah, yeah, but okay. So basically, what I'm saying is, if I take an element x in this, does this element belong to this? Let's say this is V. Does x belong to V? So if I take any general element of this thing, then what do I have? I have alpha 1 plus alpha 2 plus 2 alpha 3, right? Then alpha 2 plus alpha 3, then alpha 1 plus alpha 2 plus 2 alpha 3. This is a general vector, right? I've just multiplied with this and found out. Does this element belong to V? Can you give me some beta 1 and beta 2 such that this is equal to this? Yeah. So, do you think you can prove that now?
Yes, sir.
Okay, tell me how.
So beta 1 plus beta 2 equal to alpha 1 plus alpha 2 plus 2 alpha 3.
Right.
Likewise, three equation make and solve each other.
Okay, we have this. Then beta 2
So beta 2 equal to alpha 2 plus alpha 3.
and
Beta
the
1.
same equation again. Yeah.
Yes, sir.
So, beta 1 is essentially this. Beta 1 can be found out as alpha 1 plus alpha 3. So, basically, what we are saying is all vectors that could be achieved by some linear combination of these three can be written as a linear combination of only these two.
No, sir.
Sorry.
So now, not, we cannot find a unique value.
Why can't we find unique value?
So we take another value, we find another value like so 101 beta 1 coefficient.
The beta 1, beta 2 will change, yes. So I am saying for a particular alpha 1, alpha 2, alpha 3, I can find one particular beta 1, beta 2, right?
Yes,
Given
sir.
by this thing.
Yes, sir.
So basically a vector, so this is what? This is the linear combination of these three vectors, and this is only the linear combination of these two, right? So we can represent this column space of this as the span of only these two vectors. Is it clear or is there still some confusion? Is it clear or is it not clear?
Sir, clear.
Clear, no? Okay. So so this is basically the reachable space, subspace. So which of these options belongs to the reachable subspace?
I think, sir, all of above.
Okay, tell me how does this one belong to the reachable subspace? Give me alpha 1 plus alpha 2 such that it is equal to 1, 1 minus 1. Find out alpha 1 and alpha 2.
Sir,
Yes,
sir, alpha 2 equal to 1. Alpha 1 equal to 0.
alpha 2 equal to 1. Okay, alpha 2 equal to 1 just gives me 1, 1, 1, no?
Yeah.
Here we have a minus.
Okay, sorry, sir.
So tell me, can we find alpha 1 and alpha 2 such that this equation can be satisfied? Right, we want to find such that, tell me whether we get such alpha 1 or alpha 2 or not. Can there exist two real numbers such that this equation holds? Let's see. So alpha 1 plus alpha 2 is equal to 1, alpha 2 equal to 1, alpha 1 plus alpha 2 equal to minus 1. So is this possible?
No, sir.
Not possible. So that means this vector is not in this span.
Yes, sir.
So this vector is not reachable. Now what about these two? Give me alpha 1 and alpha 2 such that alpha 1 101 plus alpha 2 111 is equal to 222. 101 plus alpha 2 111 424. So give me alpha 1 and alpha 2 such that these two equations hold, or are they not possible like the first case as well?
Sir, alpha 2 get equal to 2, alpha 1 equal to 0.
For which case?
Sir, second one.
2 0, and for the third one?
एक minute.
Sir, alpha 1 and alpha 2 both are 2.
Both are 2. Correct. So this tells that these two belong in the span of these two vectors and thus they form a part of the reachable subspace. Okay, so for
Yes,
this
sir.
question, only these two states are reachable. Is it clear?
Yes, sir.
Okay. Okay, we'll come back to this question later if you have some time. This is, I'll just state the question first. We have a time varying system now, linear time varying system, some time varying A matrix and some time varying B matrix. We just want to find out the controllability gradient. Theoretically, it is just simple. You just have to find out T naught to T1, phi, T naught comma tau, B tau, B tau transpose, and phi, T naught comma tau transpose, D tau. Phi is given by the state transition matrix of this, but computationally it is quite time taken. So we'll come back to this after we solve the rest of the questions. So, okay. So now for these, do you know what the answers are? What do you think the answer should be?
So second and fourth.
Second and fourth.
Yes, sir.
Okay. So how do we know that?
So is lecture from lecture.
Yeah. Yeah, okay. So basically we can get to this via the proofs of by using the controllability and reachability gradients. We can show that for a continuous LTI system, the reachable subspace is equal to the controllable subspace. But for a discrete system, a reachable subspace is a subset of the controllable subspace. And this happens because if you remember, the controllability gradient for a discrete one can be written as phi t naught comma tau b tau. So the issue with this is phi t naught comma tau. So tell me what is the state transition matrix for a discrete system? Let's take just phi k comma k plus 1. Sorry, k plus 1 comma k. What is the transition matrix for a discrete system?
Forget, sir.
Okay, it is just the A matrix itself. Why? Because xk plus 1 is what? A xk plus v uk, right? And this is the transition matrix. For like for the discrete case, you can find that the A is the for a one step thing, A is the thing. But for multiple steps, it's just the product of those. So we'll have, let's say T1 comma T naught. So basically the A matrix at all time steps because it will be multiplied. And the issue is you when you write T naught comma T1, T naught comma tau, it is kind of a backward in time computation. Alright. So for that we need to in some sense find the inverse of these matrices. So one important condition is A needs to be non-singular. So only if that happens, only then can we say that both of these are equal. Or else in a general setting, only we can say that the reachable subspace is a subset of the controllable subspace. Okay, is it clear?
Yes, sir.
Okay. So we have this next question. Now we again have some continuous time LTI system. Some A matrix is given, some B matrix is given. We again want to make some comment about the reachability of the system. So tell me, how do we do this? This is very similar to what we did earlier.
So make spin and com, compare from spin value of alpha one alpha two. If alpha one alpha two exists, then is reachable. Otherwise, not reachable.
Okay, but alpha 1 some vector plus alpha 2 some vector. What are these two vectors?
Sir, 1001
Why?
considered, sir.
Sorry?
I think considered. Let assume
No, like by definition, what should these be? Like we,
linear combination exists.
yeah, just a minute. Reachable subspace is equal to what? What did we use? It is the image of the controllability matrix, right?
Yes, sir.
So what, first let us find out what is the controllability matrix.
Okay, sir. Sir,
Mhm.
1000.
So
Yeah.
this is the controllability matrix. So what is the image of this controllability matrix?
So 1000.
But what is 1000? Like how do I write it
Span.
as a span
Span.
of
Yeah. Sir, column one. Yes, sir.
these two, right?
Yes, sir.
So okay. Others also, like whenever you have doubt, please stop me immediately. These are important concepts to understand before we can understand the more complex concepts of LDS. So this is the image of the controllability matrix, correct?
Yes, sir.
But how can I simplify this? Like,
Yes.
is anyone was saying something? Okay. So how can we simplify this span? Like, so when I write span of 10 and 00, what do I write? All vectors of the form alpha 1 10 plus alpha 2 00, correct? So is alpha 2 necessary here?
No, sir.
So this we can just simply write as some alpha into 10 for all alpha in R, right?
Yes, sir.
So what is this? This is the image of the controllability matrix, right? So
Yes, sir.
the reachable subspace is also equal to the image of the controllability matrix, which is alpha 10 alpha belong to R. So this is just some constant, not infinity. So which of these states are reachable? Like which
So
of these?
one option number one.
Option number one, right? Why is this not reachable?
Raj is not in the form of one image
Yeah,
C.
it is not in this form.
Yes, sir.
Okay. So is this clear to everyone?
Yes, sir.
Okay. Okay, now we have this. So we are given this transfer function, all right, and we want to find the state space representation in a controllable canonical form. How do we do that?
सर इन कंट्रोल सिस्टम में राइट फ्रॉम सर कंट्रोल सिस्टम में पिक था तो जो डिनोमिनेटर में होता है उसका राइट साइड से माइनस लगाते हुए लिख देते हैं सर.
Okay, so tell me what the answer should be. A is equal to
सर रो थ्री सर रो थ्री लिखिए सर.
okay,
सर -4 -11 -6
okay,
सर other element sir we fill up from 1 or 0 like in row 1 1 0 0 so 1 0 0 so row 2 0 1 0 yeah 0 1 1
so is 100 then 010 011.
yes sir सही है मेरे मेरे अकॉर्डिंग.
Okay, B is
सर B no idea
okay, C.
also no idea.
Okay, anyone else?
No idea, sir.
Okay, let us see how to derive this. Okay, so
Okay sir.
we are given g of s is some y of s by u of s. We know that. Okay, y is the output, u is the input, and that is given by, let's write some general form. This is b naught s square plus b1 plus b2 by s cube plus a naught a1 s square plus a2 s plus a3. Okay, this we are given a general transfer function of the second order. Then what we do is we introduce, we introduce another variable, multiply and divide, and say that this is equal to the transfer function, right? No issues with this because we are just multiplying and dividing the same thing. Okay, then we take so this is basically we can take it to the other side and we can now write u of s is correct.
Yes sir.
Okay, then we write this in the time representation. So when I take inverse Laplace transform, what do I get here? On the left hand side, what do I have?
YT.
Yt. Let's write that as y. On the right hand side, how can I write this inverse Laplace transform of this in terms of the variable z?
No idea sir.
So this, can I write it this way? Can I write it this way?
Yes sir.
So note that this is possible because when we define a transfer function, we assume that all initial
Initial
conditions are zero.
condition 0.
So now in the same manner, how can I write u in the time for
Sir, Z 3.3 watt differentiation plus A1, Z 2 point plus A2, Z 1 point plus A3 Z.
Right. So now I'll define some states. Let x1 be z, x2 be z dot, x3 be z double dot. Okay. Then let's say this is my state. I want to make this as the state space representation. Okay. Then what is x dot? What is the value of this? Tell me. We have x1 equal to z, x2 equal to z dot, x3 equal to z double dot. So what is x1 dot?
So equal to Z1 dot
Z dot, x2 dot is
double two Z double dot Z3 मतलब X3 Z triple dot.
triple dot. Yeah. But what is z dot in terms of x?
Sir X2,
What is z double dot?
X3.
X3. What is z triple dot? Z
Sir,
triple dot we can write from this equation.
okay sir.
Z triple dot is u minus a1 z dot double dot minus a2 z dot minus a3 z. But what is this in terms of x? This is a1 into x3. This a2 into x2. This a3 into x1. So here I have u minus a1 x3 minus a2 x2 minus a3 x1. Okay. Then how can I write this in form of ax plus bu? Let's take some 3-4 minutes and then you guys tell me what A and B matrices should be. And okay, before that, y can also be written like that, right? Because y is just b naught x3 b naught x3 plus b1 x2 plus b2 x1. So what is the A matrix, C matrix, B matrix from these two equations? Tell me how can we write that?
Sir, how to start?
Okay, so let's take some. How can I write this as some A matrix into x1, x2, x3?
By finding the value of A by comparing the left hand side and right hand side.
So tell me for this particular case.
So X1
It
equal to
will be identical like this.
Right. So you see that if we have 1 0 0 0 1 0 0 0 1 into x1 x2 x3, we get x1 x2 x3, right?
Yes, sir.
Now if I say I want to write x2 x1 x3 as some A into x1 x2 x3, how can I, what should the A matrix be?
I think 0 1 0 1 0 0 0 0 1.
0 1 0
So 1 0 0
1 0 0
0 0 1.
0 0 1. Okay, yes, correct. So when you multiply first row with this, you get x2, second row you get x1, third row you get x3. So
Yes sir.
now let us write x1 plus x2, x3, x2 plus x3. How can I write this as AX? How can I write this?
Sir, 110
110
001
001
011.
0. Correct. So you get the gist of it, right? Like you just see left hand side what terms are there and how many times, like, because each each element here is just a linear combination of these three. So that linear combination decides this row vector for me. Correct. So x1 plus x2 is the linear combination of x1, x2, x3 with the coefficients for x1, x2 as 1 and that for x3 as 0. So that decides the first row for me. Similarly, this is a linear combination of this, but only with coefficient 1 for x3 and 0, 0 for x1 and x2. So that is how we get this A matrix. So based on that, how can we write this x2, x3 and u minus this whole term as ax plus bu? Okay, x dot is some 3 cross 3 matrix into x. X is highlightful, x1, x2, x3, and this will be b will be some 3 cross 1 matrix because we have only one input. So yeah, so how do I write a and b?
Sir, 010
0 1 0
001
0 0 1
9 alpha 1 plus alpha 2. Sorry, alpha 1, alpha 2, and sorry, A1, A2, and A3.
Okay,
So we sign
sign up.
And
minus A1, minus A2, minus A3.
And on the b matrix
111.
1 1 1. Okay, so let's see what these equations give us. X1 dot is equal to what? From first row, x2 plus u. So is this correct?
No, sir.
Then what?
0.
So you column 001.
0 0 1. So now we have x1 dot is x2, which is correct. X2 dot is x3, which is correct. Now x3 dot was it? What is it? As per we have written, it is minus a1 x1 minus a2 x2 minus a3 x3 plus u. Is it correct?
No, sir.
So what change should we make?
So in the place of the minus A1, we put minus A3. In place of the A3, A1, yes, sir. Now it's correct.
So this is what we were telling earlier. The trick is, once you know this derivation, it becomes very simple. Like you can use it anytime you want. But as a trick, this is A1, A2, A3. This is B0, B1, B2. So, okay, we have not gone till that part. First, let us find out C as well. What is C? From this, we can find it out. What is C?
So, B2,
B2.
B1, and B0.
Correct. So, this is the C matrix. So, basically, this is A, this is B, this is C. So, for this particular question, what should be the A matrix?
So 010,
0, 1, 0, then
001,
right, then
minus 4,
minus 1,
minus 11,
minus 11,
minus 6.
minus 6, then
So B matrix 001.
0, 0, 1, then
So C matrix 5,
5,
1 2.
Correct. So this is basically how you find out a transfer function, like from a transfer function, how you go to the state space representation in controllable canonical form. Is it clear?
Yes, sir.
Okay, so then do you want me to solve this question or do you want to try it out for yourself? Like, this is theoretically, you don't have anything new, you just find these matrices and then go ahead. Do you want me to do it or do you want to try it for yourself? I can also do it if you want. Just tell me which one do you prefer?
Sir, you can solve.
Okay. So the main first challenge in this is to find out the state transition matrix, right? Then
Yes, sir.
let us, so first let us write these equations. Okay. X dot equal to AX plus BU, right? So first, so how do we obtain the state transition matrix? One way to
Sir,
do it is just take X dot equal to AX and find the solution of X of t in this in terms of some matrix into X naught. Then this matrix will give me the transition matrix t comma t naught. Okay, so let us try with that way. So x dot equal to ax means x1 dot equal to minus x1 plus e to the power 2t x2 and x2 dot equal to minus x2. Is it clear?
yes, sir.
So first tell me the solution for this.
सर
Tell me.
सर आपने वो क्यों नहीं यूज किया एस आई माइनस ए इनवर्स स्टेट ट्रांजिशन मैट्रिक्स के लिए?
वो बस एलटीआई सिस्टम्स के लिए होता है.
ओके.
For LTV systems, the usual process can become lengthy, so we directly try to find it. So tell me what should the solution of this, because this one we don't have any x1 term, this is just like a scalar differential equation. So what is the solution for such a differential equation? Normal high school calculus से जो सीखे थे.
सर गिव मी 1 मिनट आई टेल यू.
Yeah, yeah.
सर हेलो.
Tell me.
सर एलन एलन एक्स टू.
Sorry, sir. X2.
सर एलन एक्स टू. सर लॉग एलन
Okay. X2 is equal to.
माइनस टी some constant.
So this is x2 is some k into e to the power minus t.
या
So what is k?
constant value.
But how can we find out k? From, because we know the initial condition x naught is equal to some x1 naught and x2 naught. So how can we use this to find out k? So x2 of t is k into e to the power minus t. But x2 of 0 is x2 naught. So how do I find it out? So what is the value of k? Okay, so x2 of t is this. So x2 of 0 is what? K into e power 0, which is k. But that we know is equal to the initial condition x2 naught. So x2 of t is equal to x2 naught into e power minus t. Okay, then so x1 dot equal to minus x1 plus x2 naught into e to the power t. Correct?
Yes, sir.
So now how do I solve this?
So by using integrating factor,
Okay, tell me how.
so by using integrating factor, Lagrange, I think, apply.
Okay, let's take it this side. So then I can multiply this. So this is d by dt, right? Is this correct?
Yes, sir.
So then I have x1 dot, sorry, what did I have? X1, e to the power t x1 is equal to integration x2 naught e to the power 2t dt for 0 to, for t naught to t1, let's, for 0 to some t1, let's take. Okay, let's just take for t. So this is e to the power t x1 of t minus x1 naught, which is x1 naught, is equal to x2 naught e to the power 2t by 2, 0 t. So this is x2 naught by 2 e to the power 2t minus 1. So x1 of t is equal to x2 naught by 2 e to the power t minus e to the power minus t. So what is this? X2 naught sin h t. Correct?
Yes, sir.
No, no. We have missed this term.
Yes.
So now I have x1 of t as this and x2 of t I know as, what did we find out? X2 naught e to the power minus t. So what is the transition, like how can I write x1 of t, x2 of t is equal to some matrix times x1 naught, x2 naught from these two equations.
So e power minus t
E power minus t
sin h t
sin h t
0
0.
e power minus t.
Correct. So this gives me the phi t comma 0 thing. Okay.
Yes, sir.
So similarly, I can find out for phi t1 comma t naught. Like instead of 0, I could have taken some t naught here. Same thing, same process. Just instead of 0 and t, I can take t naught and t1, and then I can find, or rather to say, like for this we need t naught comma tau, right? So I can take the time values accordingly and then find the transition matrix that I get that takes a particular state in tau, time tau, to a particular state in time t naught. So by doing that, I can then find out. So one thing is you cannot find out directly using this process T naught comma tau, but you can find out using this process tau comma T naught, because tau is greater than T naught. Starting time is T naught. So then you take the inverse of this matrix. Okay. Then you just plug it into here and you can directly get the answer. Okay. So for today, we'll do that many questions. And does anyone have any doubts?
सर
Tell me.
सर हमें क्वेश्चन पूछना था दो.
Ask us.
सर असाइनमेंट का क्वेश्चन सर हम कर रहे हैं सर, समझ में नहीं आया सर, ये बता सकते हैं सर?
कौन सा?
सर एक क्वेश्चन है सर, वो दिया हुआ है कि दो पेयर हैं ए बी,
ए बी
ये दोनों सब कंट्रोलेबल हैं.
कंट्रोलेबल है.
बोल रहा है कि बीटा अज्यूम कर लीजिए कि ग्रेटर देन जीरो है.
बीटा.
यस सर.
ओके.
सर क्यू इक्वलेंट टू इंटीग्रेशन फ्रॉम जीरो टू बीटा.
वेट वेट. क्या क्या? क्यों?
सर क्यू इक्वल टू इंटीग्रेशन फ्रॉम जीरो टू बीटा
बीटा
ई का पावर माइनस टी ए ट्रांसपोज. सर टी के मल्टीपल में, सर टी के मल्टीपल में ट्रांसपोज. यस सर. बी, सर बी, बी ट्रांसपोज सर ई का पावर माइनस टी ए ट्रांसपोज डी टी.
ओके.
सर इसमें फोर ऑप्शन है, हमने दो ऑप्शन एलिमिनेट कर चुके हैं सर. इसमें पूछ रहा है कि द मैट्रिक्स ए, सर मैट्रिक्स ए माइनस बी बी ट्रांसपोज क्यू, सर क्यू इनवर्स मतलब क्यू को पावर माइनस वन. सर ये सर बी बी ट्रांसपोज से मल्टीपल होगा ये. यस सर. इज हुरविज पूछ रहा है सर.
क्या पूछ रहे हैं?
इज हुरविज एच यू आर.
सर सर आई डिडंट हियर इट. रिपीट वंस मोर.
सर हुरविज पूछ रहा है सर, दिस मैट्रिक्स इज हुरविज, राउथ हुरविज.
अच्छा अच्छा.
जस्ट लाइक.
ये कौन से असाइनमेंट का क्वेश्चन है?
सर वीक फोर सर.
अच्छा, वीक 4 का है तो वो तो हम नेक्स्ट टाइम में डिस्कस करेंगे, क्योंकि सबमिशन के बाद ही कर सकते हैं.
सर बस हमको ये पूछना था कैसे सर इस पार्टिकुलर चीज से जानेंगे कि हुरविज है. अगर सर कोई इक्वेशन होता है जैसे हमारे पास मैट्रिक्स होती है तो हम तो वो बना के सर सॉल्व कर सकते हैं, क्योंकि फर्स्ट रो सॉल्व पॉजिटिव आ जाता है तो उससे हम पता लगा लेते हैं. मगर सर फ्रॉम इक्वेशन से कैसे करते हैं, कोई स्टार्टिंग कैसे करें?
मतलब ये जो मैट्रिक्स है उसको हर्विट्स है या नहीं दिखाना है.
यस सर. कैसे करेंगे ये सब टाइप?
कैरेक्टरिस्टिक इक्वेशन निकालना पड़ेगा.
सर क्या निकालेंगे?
कैरेक्टरिस्टिक इक्वेशन जो आइगन वैल्यू के लिए जो निकालते हैं.
सर इसमें कोई मैट्रिक्स नहीं है तो कैसे निकालेंगे?
ये मैट्रिक्स दिया है ना.
तो सर यहाँ पे मैट्रिक्स ए बी सी अपने से ज्यूम करेंगे.
नहीं नहीं, अपने से अज्यूम नहीं करना है. कीप इट एज इट इज.
ओके.
ऐसे करके लैम्डा आई माइनस ए प्लस बी बी ट्रांसपोज क्यू इनवर्स देन
इक्वल टू जीरो.
इक्वल टू 0. ये फाइंड करने की कोशिश करो.
ओके सर.
मोस्ट लाइकली यू कैन शो सम जनरल रिजल्ट. मतलब ए बी जानने की जरूरत नहीं है. फॉर एनी कंट्रोलेबल ए और बी कुछ एक दिखाया जा सकता है. तो ट्राई दैट. देन इफ नॉट, इफ यू कैन नॉट सॉल्व इट, देन विल डिस्कस इट.
सर एक क्वेश्चन और.
हाँ.
सर स्टेबलाइजेबल कैसे निकालते हैं, बस थोड़ा सा हिंट टाइप में कैसे? सर थ्योरी में समझ में नहीं आया था सर.
सो स्टेबलाइजेबल एसेंशियली है कि सो
सर कंट्रोलेबल, सर कोई मैट्रिक्स दी हुई है तो उससे हम कंट्रोलेबल निकाल लिए हैं, तो पूछ रहा है कि सर इस कंट्रोलेबल से वो मैट्रिक्स नहीं थी तो पूछ रहा है कि ये स्टेबलाइजर है कि नहीं है, तो सर कैसे निकालेंगे?
सो स्टेबलाइजेबिलिटी के लिए हमको लाइक फर्स्ट थिंग, स्टेबलाइजेबल का मतलब क्या है?
सर अनकंट्रोलेबल मतलब रैंक जो आती है हमारी कंट्रोलेबल में इक्वल नहीं होता, इसलिए स्टेबलाइजर पढ़ते हैं. जो फुल स्टेबलाइजर मतलब फुली अनकंट्रोलेबल नहीं है, समथिंग पार्ट उसका स्टेबलाइज स्टेबल है.
हाँ, तो मतलब क्या है उसका?
सर नहीं पता.
तो स्टेबलाइजेबल मतलब है कि if you have a system
Okay.
and there are some controllable eigenvalues, there are some uncontrollable portions.
Yes, sir.
Okay. So controllable portions can be like the eigenvalues corresponding to the controllable part can be positive or non-negative,
Yes, sir.
or the eigenvalues corresponding to uncontrollable part must be negative. So what happens from this is, since you can control the controllable part as you want, the controllable eigenvalue can be placed anywhere as per our desire. But if the but we cannot do that with the uncontrollable part. So if the uncontrollable part has a negative eigenvalue, that means the system will at least not blow up. So for the controllable part, we can control as we want, place the eigenvalues wherever we want. But for the uncontrollable part, if it is negative, the eigenvalue is negative, then the entire system is told as stabilizable.
Okay, sir.
मतलब roughly idea यही है, but you you can find that stabilizability by doing a controllable decomposition. Is it taught to you in class?
Yes, sir.
So use that and then we can discuss if you are not able to solve any problem.
Okay, thank you, sir.
Okay. So if there are no more doubts, maybe you can stop for today's session.
So when will be the next session?
I'm sorry.
Monday.
Yeah, yeah. The next session will be
Mon-
every week Monday, same time.
Okay, sir.
Yeah. So thank you.
Thank you, sir.
Thank you, sir.